Most HVAC systems are designed to move heat. A cooling system removes heat from a building and sends it somewhere else. A heating system adds heat to a building when the space needs to be warmed. But in many commercial buildings, something interesting happens. One part of the building may need cooling at the exact same time. Another part of the building needs heating. An interior office zone may need cooling because of people, lights, computers, and equipment. At the same time, the perimeter of the building may need heating because the outside air is cold. A hospital may need cooling for interior spaces, imaging rooms, laboratories, and equipment areas, while also needing heat for reheat coils, domestic hot water, and ventilation air. A hotel may need chilled water for guest rooms, corridors, kitchens, and meeting spaces, while also needing domestic hot water for showers, laundry, kitchens, and cleaning. In a conventional system, the chiller removes heat from the building and rejects that heat through the condenser water system and cooling tower. At the same time, the boiler may be burning fuel to create heat somewhere else in the building. So, the building is paying to remove heat from one place, and then paying again to create heat in another place. A heat recovery chiller changes that story. Instead of treating condenser heat as waste, a heat recovery chiller captures that heat and sends it to a useful heating load. That is the basic idea. In this video, we'll look at two heat recovery chiller designs. Now let's look at the first application. In this application, the heat recovery chiller is used to lower the condenser water supply temperature feeding the main chillers. Picture a central plant with several large water-cooled chillers. The main chillers are connected to a condenser water loop and cooling towers. Under normal operation, condenser water leaves the cooling tower and flows to the chillers. The chillers reject heat into that condenser water. The warmer condenser water then returns to the cooling tower, where the heat is rejected outdoors. The temperature of the condenser water matters. When the condenser water entering the chiller is cooler, the chiller usually has an easier time rejecting heat. The compressor does not have to work as hard, and the chiller can operate more efficiently, as long as the temperature stays within the manufacturer's allowable operating range. Now imagine adding a heat recovery chiller into this plant. The heat recovery chiller can be arranged so that it removes heat from the condenser water loop before that water feeds the main chillers. The condenser water enters the heat recovery chiller at a warmer temperature. The heat recovery chiller removes heat from that water. The condenser water then leaves the heat recovery chiller at a lower temperature and continues onto the main chillers. From the main chiller's point of view, they are now receiving cooler condenser water. That can reduce compressor lift and improve chiller efficiency. But the heat removed from the condenser water is not wasted. The heat recovery chiller captures that heat and sends it to a useful heating load. For a diagram, picture this system in three sections. The condenser water gives up heat to the heat recovery chiller. The heat recovery chiller sends that recovered heat to the hot water loop. The condenser water continues to the main chillers at a lower temperature. The main chillers operate with cooler condenser water. The heating system receives heat that would otherwise have been rejected outdoors. This type of application can make sense in a large central plant where the facility has both cooling and heating needs throughout the year. A hospital is a good example. Hospitals often have interior cooling loads from people, lights, medical equipment, imaging rooms, laboratories, and ventilation requirements. At the same time, hospitals may need hot water for reheat coils, domestic hot water, perimeter heating, and air systems that maintain pressure relationships between spaces. Without heat recovery, the hospital may reject heat through the cooling towers while the boilers are operating to provide heat somewhere else. With heat recovery, some of that heat can be captured and reused. This can reduce cooling tower load, reduce boiler load, and improve the overall efficiency of the plant. This first application is not just about one chiller. It is about optimizing the whole plant. The heat recovery chiller helps the main chillers by lowering the condenser water temperature, and it helps the heating system by providing recovered heat. Now let's look at a second application. In this case, the heat recovery chiller directly produces chilled water for a cooling load and recovered heat for a heating load. This is probably the easiest application to understand. The chilled water leaves the heat recovery chiller and flows to a cooling load. That cooling load could be an air handling unit, a data room, an electrical room, a laboratory, an interior zone, or another piece of equipment. The chilled water absorbs heat from that load and returns warmer to the chiller. Inside the evaporator, the refrigerant absorbs the heat from the chilled water. The compressor raises the pressure and temperature of the refrigerant. Then the condenser transfers that heat into a hot water loop. That heating load could be reheat coils, perimeter heating, domestic water preheat, makeup air heating, or another system that needs heat. The hot water gives up heat to the load and returns cooler to the heat recovery chiller. The cycle continues. The chilled water side removes heat from one part of the building. The hot water side delivers that heat to another part of the building. The chiller is doing two useful jobs at the same time. It is cooling one load and heating another load. This is why heat recovery chillers are often compared to water-to-water heat pumps. They move heat from a lower temperature water loop to a higher temperature water loop. The cooling load becomes the source of heat. The heating load becomes the place where that heat is used. A good example is an office building with interior zones that need cooling even during mild or cool weather. Interior spaces can stay warm because they are surrounded by other conditioned spaces and filled with people, lighting, computers, and equipment. At the same time, the perimeter zones may need heating because they are exposed to outdoor conditions. A heat recovery chiller can remove heat from the interior zones and deliver that heat to the perimeter heating system or reheat coils. The system is not creating heat from nothing. It is moving heat from where it is not wanted to where it is needed. A heat recovery chiller removes heat from a cooling load and delivers that heat to a heating load. It does not just make chilled water. It manages heat. And when the application is right, it can reduce boiler runtime, reduce cooling tower load, lower energy use, and improve the overall performance of the central plant. To understand how this works, let's first look at a normal water-cooled chiller. In a typical chilled water system, chilled water leaves the evaporator side of the chiller and flows out to air handling units, fan coils, process equipment, or other cooling loads. As the chilled water moves through the building, it absorbs heat. The water returns warmer to the chiller. Inside the evaporator, refrigerant absorbs that heat from the chilled water. The compressor then raises the pressure and temperature of the refrigerant. The hot refrigerant moves to the condenser, where the heat is transferred into the condenser water loop. The condenser water carries that heat to the cooling tower, and the cooling tower rejects it outdoors. So in a normal system, the path is simple. Heat comes out of the building. The chiller moves the heat into the condenser water. The cooling tower rejects the heat to the atmosphere. That works, but it also means the heat is wasted. A heat recovery chiller uses the same basic refrigeration cycle, but the application is different. Instead of sending all the condenser heat to the cooling tower, the heat recovery chiller transfers useful heat into a hot water loop. That hot water can then be used for heating coils, reheat coils, domestic hot water preheat, perimeter heating, makeup air heating, natatorium heating, process water heating, or another useful load. The evaporator side still produces chilled water. The condenser side produces useful hot water. That is what makes the heat recovery chiller different from a standard chiller. It has two useful outputs. On one side, it provides cooling. On the other side, it provides heating. This is why a heat recovery chiller should not always be judged the same way as a normal chiller. A standard chiller is usually judged by how efficiently it produces chilled water. But a heat recovery chiller may be producing chilled water and useful hot water at the same time. When both sides are doing useful work, the combined value of the machine can be much greater than looking at cooling alone. In simple terms, the building gets cooling from the evaporator side and heating from the condenser side from the same machine. That is the value of heat recovery. But there is one important rule. A heat recovery chiller works best when there is a cooling load and a heating load at the same time. If the building needs chilled water but has no useful place to send the recovered heat, then the heat still has to be rejected somewhere. That may be a cooling tower, fluid cooler, dry cooler, or another heat rejection device. And if the building needs heating but does not have enough cooling load available, then the heat recovery chiller may not have enough heat to recover. This is why heat recovery chillers are commonly considered for hospitals, campuses, laboratories, hotels, high-rise buildings, central plants, and facilities with year-round interior cooling loads. These buildings often have simultaneous cooling and heating needs. They are removing heat from one part of the building while adding heat to another part of the building. A heat recovery chiller connects those two needs. Instead of throwing heat away outdoors, the system asks a better question. Can we use that heat somewhere else? Now let's talk about operation. Some heat recovery chiller systems operate in cooling priority. That means the chiller runs mainly to satisfy a chilled water load. If there is a useful heating load available, the system recovers heat. If there is no heating load available, the system may reject the excess heat through a tower, fluid cooler, or other heat rejection device. Other systems operate in heating priority. That means the heat recovery chiller runs mainly to satisfy a hot water demand. The chilled water becomes the useful byproduct. This can happen in a campus system where the chilled water can be used somewhere else, even if the local building does not need all of the cooling. Some systems can operate in either mode depending on the time of year, the utility rates, the heating demand, the cooling demand, and the plant sequence. The important point is that the controls must decide what the system is trying to accomplish. Is the heat recovery chiller running because the building needs chilled water? Is it running because the building needs hot water? Is it running because both loads are available? Is excess heat being rejected? Are the boilers enabled? Are the cooling towers enabled? These control decisions are what make the system work. The refrigeration cycle may be familiar, but the plant sequence can be more involved than a standard chiller plant. This is why heat recovery chiller systems need good design, good controls, and clear operating intent. Bigger is not always better. A heat recovery chiller needs somewhere to put the heat. If you found this video helpful, be sure to check out our HVAC and plumbing estimating spreadsheets to streamline your construction bidding process. Check out our HVAC, electrical, and plumbing construction forms to help you run your business, and explore our online courses for in-depth training.